Hello students, welcome to video lesson 7.1. We're going to start chapter 7 today with some review of some stuff that we did back in Algebra 1. We're going to talk about ratios and proportions. Now proportions is something that I believe we are all somewhat familiar with and can handle proportions because we've been doing them for a long time, solving things like 3 over 4 equals x over 7, something like that, cross multiplication and all that fun stuff. So we're going to sort of skip over that part of this section, but we are going to review things about ratios, how we can write them, how we can simplify them, how we can use them to answer questions, and then we'll also talk a little bit more about proportions, some properties of them, some things that we can do with proportions to potentially make life easier in certain situations. Okay, so if we start just with a quick review of what a ratio is, a ratio is defined as just the comparison of two quantities, and there are 3 different ways that we can write a ratio. Okay, most often we see them as fractions because that's the easiest to deal with mathematically. We do often see them with a colon in between, just those 2 dots, or we can just go ahead and use the word to, A to B. Okay. All of these are read that same way, A to B or A to B, A to B. But there's 3 different ways you can write them. Like I said, we will mostly see the fraction version right here. Your problems in your homework will often be written with the colon version, these 2 dots. We don't often see this in math class, but we could. Okay, and you can write a ratio that way if you choose to do that. It is important normally, unless you're talking about some sort of conversion rate and things like that, we usually express the ratio in the same units, and then we simplify it down as far as we can, like we do with all fractions. Okay, so here's an example of something that we might have to do in terms of adjusting units and things like that when we're writing a ratio. This says a bonsai bald cypress tree is a small version of a full-size tree. Okay. So a cypress tree can grow to be 118 feet high, okay, 118 feet tall. This bonsai tree here is a smaller version of that, and that's 15 inches high. They want to know what is the ratio of the bonsai tree to the height of this gigantic cypress tree in Florida. Okay, so what I want you to first notice is they're just asking me to really write a ratio. So I'm just going to write it sort of like this, 15 inches. And then I'll do the fraction version, 118 feet. Okay, so this would be totally fine in terms of a ratio if these were the same units, but currently they're not the same units. So what I'm going to do is I'm going to convert the inches into feet. Okay, I'm going to change the inches to feet, and then I'm going to try to maybe rewrite the ratio a little bit. Okay, so 15 inches turned into feet. To turn inches into feet, we should divide it by 12, right? Divide it by 12, and we actually get 1.25. So it's 1.25 over 118. Okay, that's my ratio. And writing it in simplest form, if I wanted to simplify the ratio, that just involves changing the top number so that it's no longer a decimal. Okay, so what I'm actually going to do is I'm going to multiply the top by 4 and multiply the bottom by 4 as well. And the top number is going to be a 5. And the bottom number is going to be 118 times 4 is 2, carry 3, 4, 7, 472. 472. Okay, so this ratio right here, 5 to 472, is my ratio of the bonsai tree's height to the height of the big tree. So as you can see, writing a ratio is not difficult, but changing it to be in its simplest form can be slightly difficult, okay? I don't think, you may not see one exactly like that, but that's sort of the idea behind, if I write a ratio, are the units the same, okay, in my 2 quantities, and is it in simplest form, meaning no decimals and no common factors for the top and the bottom. Okay, so that's writing a ratio. It's actually more applicable for us in geometry class to use algebra with ratios. And so I'm going to go through this word problem real quick, and then I'll show you a geometry example which uses what we call an extended ratio. So members of this school's band are buying pots of tulips and pots of daffodils to sell at their fundraiser. They plan to buy 120 of them total, 120 total pots. The ratio is going to be 2 to 3 for tulips to daffodils. So basically what that means is for every 2 pots of tulips, they're going to buy 3 pots of daffodils. Okay, so they buy 2 of these, 3 of these, and they're going to keep going, keep going, keep going, keep going. The question is, how many of each type are they going to buy to get their total of 120? Okay, so we have this ratio, tulips to daffodils, 2 to 3. And what I can do is, I don't know exactly how many of each one they're going to buy, but I do know that the number of tulip pots they're going to buy is a multiple of 2, right? Because they're going to buy 2, and then 3 of these, and then 2 more, and then 3 of these, and then 2 more. So it's going to be multiples of 2, the number of tulip pots that they do, or that they buy. And then the number of daffodil pots is going to be a multiple of 3. So you can see what we do here is we just put an X on each of the numbers from our ratio, and that tells me the total number of tulip pots. I don't know what X is, but I'm going to figure it out shortly. And 2 times that number is going to tell me the number of tulip pots, and 3 times that number is going to tell me daffodils because of this ratio 2 to 3. Okay, so I put an X on each number in the ratio, and then when I combine them together, the total number of pots they're going to buy is supposed to be 120. So I end up with this equation here, 2x plus 3x. That's the number of tulip pots plus the number of daffodil pots. Total together have to be 120. Okay, so 2x plus 3x is 5x. So 5x equals 120 gets me to x equals 24. So I know that x is equal to 24, and that allows me to find the number of tulip pots and the number of daffodil pots, because 2 times 24 gives me 48 tulips, and 3 times 24 gives me 72 daffodils, okay? So from the ratio, I was able to write an algebra equation and solve the problem in that way, okay? Okay, so if we look then at a geometry example of this same kind of thing, we end up using a lot in geometry class what we call an extended ratio. Okay, an extended ratio is basically a ratio of more than 2 numbers. Okay, it actually relates 3 or more numbers or quantities together. And when we write extended ratios, we have to write them with the colon version. Okay, so we have to write them in this way because a fraction of 3 numbers doesn't really make any sense. So we always write our extended ratios in this format. Okay, and that's how you're going to see your book doing it. And then we can basically do exactly the same thing we were just doing and answer questions using these ratios. All right. So this particular problem says the lengths of the sides of a triangle are in this extended ratio, 3 to 5 to 6. 3 to 5 to 6. The perimeter of the triangle is a total of 98 inches. What is the length of the longest side? Okay. So we can actually find the length of all the sides, but they're specifically asking us for the longest in this case. So the lengths of the sides of a triangle are in this extended ratio. So remember, when we have things in a ratio, we can write each of them algebraically, right? Because we don't know what the smallest side is, but we do know that it's going to be 3 times something. Right? Because we know it's going to be a multiple of 3 because it's in this ratio 3, 5, 6. I know that the middle side is going to be 5 times something, and I know that the last side is going to be 6 times something. Okay, so I have this type of picture where I have one side that's 3 times some number, one side that's 5 times some number, and 6 times some number is my longest side. So if I write each of these algebraically, and then I think about what it means to have the perimeter be 98. The perimeter of a shape, perimeter of a triangle, well, that should just involve adding these 3 side lengths together, and it needs to equal 98. Right? And now this is an algebra equation that hopefully we can solve. 3 plus 5 plus 6 makes 14x equals 98. If I divide away the 14, I believe I get x equals 7. Okay, x equals 7. 7 times 14, 17, 20. Yep, right. So x equals 7 is the answer to this equation, but it's not actually the answer to the problem, right? The problem asks what is the length of the longest side. So they're asking me specifically about this side here. And I know now that x is 7, so if I do 6 times 7, 6 times 7 gives me 42. So this is 42. And I do know the units because they told me 98 inches, so I suppose I could say it's 42 inches if you want. But that uses, like I say, an extended ratio of more than 2 numbers algebraically to solve a geometry problem. Okay, so we're going to have to do that sort of thing in our homework as well. You'll also see things about angles that are supplementary, like maybe supplementary angles that have a ratio of 2 to 5. So we just do 2x plus 5x equals 180 degrees. Then we can solve that equation, all right? So that's all you're going to be asked to do with ratios, is use them algebraically, possibly write them or simplify them down. The rest of this section is about proportions. And just as a quick review, a proportion is any time 2 ratios or 2 fractions are set equal to each other. So we end up with something like this. Okay, so we have one fraction, one ratio A to B is equal to this other ratio C to D. So when we solve these, generally what we would do is we would cross multiply, right? We do A times D, we do B times C. We'd set those equal. A times D is equal to B times C, okay? And this is something that we have been doing, I think, a lot in our mathematical career. So if you aren't sure about this, do some refreshing on your own about solving proportions. But what we're going to talk about are actually some properties of proportions and what we can do with them to potentially make our lives a little bit easier. So your book uses some vocabulary for these different things that we multiply together. So if I go back to maybe the colon version, it's a little easier to see. A to B is equal to C to D. Okay, and your book then highlights the A and the D and calls those the extremes. Okay, the extremes because they're on the outside of these ratios. And then C and B, they call the means because they're sort of in the middle. Okay, so that's the sort of language that they use here, or we can use here, I suppose. So 3 properties of proportions that allow us to sort of change things around and see the proportion in a slightly different way, which may help us when we get to solving some more complicated proportions and things like that. All right. So the first property, which is highlighted here, I'll go back to this. The first property here is that you can reciprocate both of the fractions and it's still the same proportion. Okay, so all of these are basically going to be saying, what can I do to a proportion to keep it exactly the same? Okay, so I can flip the 2 fractions around and it is exactly the same thing. Okay, and that we should be able to see that because I'm still doing A times D, right, when I cross multiply, except I'm doing it, either this way or this way. And I'm still doing B times C. It doesn't change anything about what I'm multiplying when I solve. So it's perfectly okay to flip both of the ratios to their reciprocals and keep the proportion exactly the same. We can also flip around the extremes or the means and keep the ratio exactly the same. So specifically here they say you can take the bottom number of the first ratio and the top number of the second and flip them around and you get the same thing, right? Because it doesn't actually matter if you do B times C, right? B times C, or if you do C times B. It doesn't matter which order you multiply them in, so you can flip those around in the proportion and it's exactly the same thing, okay? And then finally, the third property of proportions is that we can add the denominator to the numerator on both sides, and it keeps exactly the same ratio. Okay, it's basically, you guys, adding 1 to the whole fraction, okay, to the whole ratio. And as long as I add 1 on both sides, it doesn't really matter. Okay, so I can do that here. Here you notice they've added b on the top of the left side, and they've added d on the top of the right side. So they take the denominator and just add it on the top, take the denominator, add it on the top, you get something that is equivalent, all right, exactly the same. So what we're gonna have to do with this is we're gonna have to sort of answer questions like this. Okay, so in this diagram, they tell us, this one over here, x over 6 as a ratio, x to 6, is equal to y to 7, okay? And they want us to sort of rewrite this in a different way. They want actually a ratio for x to y. They want a fraction ratio for x to y. Well, notice that if I flip around the y and the 6, I'll have exactly what they want on the left-hand side, right? I'll have the y then on the bottom underneath the x, and then the 6 just flips position to be here, so we end up with this, x over y equals 6 over 7. Okay, so we can use these three properties of proportions to rewrite things to get more numerical fractions like this and find equivalent proportions and the like. All right, as we continue in chapter 7, we're going to be applying ratios and proportions to what we call similar polygons, and specifically similar triangles most of the time. So you're going to see a lot more pictures like this. You're going to be applying proportions to a lot of different situations and a lot of different scenarios. So it's important to be sort of up to speed on proportions, what they look like, what we can do with them, and how we can use them to answer questions. So if you have any questions about any of these things, proportions, ratios, or equivalent proportions or anything like that, please reach out to me before we really get into the heart of chapter 7. If not, that's all I have for you today, and we'll talk to you soon.